Other Tom is here as well, but
make sure we're there. Alright, good afternoon everyone. Welcome to our second lecture of week 8. Hope you're all doing well. You've probably heard the not so good COVID news yet again this morning, so I hope you're coping well working like this, because we may be doing this for a little while. Alright, so where are we? As usual, we've got a weekly test due. The last week's test is due today at I can't remember what the due time is. Is it 6 o'clock? I can't remember when it is this afternoon, but there's a weekly test due this afternoon, straight after this lecture, and the next weekly test will be out later today or first thing tomorrow, depending on how things are happening. In bigger news, I guess, assignment 2 is out. I think there's one or two things being polished up about auto tests. Maybe not all the auto tests are working yet, not that really matters, but Zoe, who was the assignment author, and Tom, who assisted, did a live stream yesterday, which I understand went well. It's been put up on the class lectures page, so if you didn't catch it live, it's there on the class lectures page. So maybe read the assignment spec and watch it. But let me strongly emphasize the advice I made with assignment 1. Don't set aside 2 days before the assignment due date 16 hours to work on the assignment. No, don't do that. Start doing now. Put in half an hour in today, half an hour in tomorrow, maybe more on the weekend. You'll need to attack it for a while. You'll hit something, then you'll have to read about it or ask your tutor about it, or wait until you see something in a tute and then come back and do more and more. So you should be revisiting the assignment over and over again in the upcoming 2 weeks. Alright, so that's the assignment. I think that's all we had to talk about then, so we can go straight into the lecture content. So today's lecture is just more on linked lists, and this week's lab exercises and next week's lab exercises both on linked lists as well. So on screen is where we finished. So we've been working through linked list in it's a nice context of a game. So what were we doing? Remember, the crucial thing in these linked list data structures is this pointer, which can point to a struct of the same type. So we can create 1, 10, 50, a million of these structs and link them together with this pointer. So this one, we're using the chain them together in the pointer. You could use pointers to create all sorts of interesting and amazing structures, but we're just going to work with lists where they're chained one after the other, and there's a special case when you get to the last one, that field will contain null. Now on these, also in the struct will be whatever work we're doing, whatever particular task we've got. What's there will depend on that. So in lots of coding examples, we just put an int there, so you just put an integer in there. But we've got a real example here. So in fact, what we've got is a player name stored in there, an array. So that's our payload, what we're actually working with, the information we want to keep a list of. Now, let's see what we did. And there's a special variable we need for every linked list, as well as the structs, as well as each struct for the list elements. We need to keep somewhere a variable that contains a pointer to the first thing in the list. If you can get to the first thing in the list, you can get to everything in the list by successively following next pointers. But you've got to have that pointer to the first thing in the list. What do I mean by that? I think I've got a slide here showing you what the story is. Oh no, that's creating. Let's go back still to a picture. There's a picture of a list. If I can get to this one, I can use its next pointer to get to the next one, its next pointer to get to the next one, its next pointer to get to the next one, and then I'll find null in here and stop. But I've got to get to the first one, so I've always got to track this first list node. Often we call that head. No reason you could call it first if you wanted, but head is what often gets called by coders. So we've called our variable head. Print players it prints out the players we've got, but it's a great example of a loop that executes once for each item in the list. So let's go look at that, which will be right down the bottom. Oh, actually, before we do, we should look at create player. This is what we're using to create one of these structs. How does it work? It's given the name of the player and whatever should be the next field for this struct. Uses malloc to get enough memory to hold the struct. We keep calling size of. Initializes those fields. Oh, in this case, that's sort of nice, isn't it? We can't use an assignment because we've got to fill in a whole array. But because it's a char array that's zero terminated, we can use string copy to do the job for us. So that creates one of our players. Let's just go. I'll just go back and show you those calls. There are those calls. So that creates a list containing 4 elements, which will be Anusha, Shrey, Chicken, and Mark. We'll come back. We'll come on to Zoe shortly. Zoe is different. But let's have a look at print players. Print players is easier to understand. So let's recap it, make sure we understand it, then we'll move on to where we were up to when we left off. Print players is a classic example of a loop that executes once for each element in the list. Really important code, super important code. We'll give you a couple of chances to practice this in lab exercises. So there was a lab exercise this week, and there's a lab exercise next week that use exactly this style of loop. We use a pointer to move down the list. We set the pointer to point to the first thing in the list. Every time we want to move to the list element, we say make the pointer point to whatever's in the next field of the thing it points at. We know when to stop when the pointer contains null. And here we've got just a little printf, but that could be anything. So you'll do lab exercises where that has something different in there. That might be an if statement, it might be some calculation, who knows. But line 41 would become some sort of code. All right. Now, there's a good question in the chat from Brandon saying, well, is this condition there always going to be just that condition? No. This is the sort of the simplest and most fundamental condition you could have, but you could have more complicated conditions there. Not if you want to do things other than just loop through all of the things in the list. You might want to stop before you get to the end of the list, in which case you might use a different condition there. And you might want to nest this. Next week's lab, I think, has exercises. Yes, next week's lab has exercises where you have to nest this, which gets to be also fun. All right. So I've modified this a tiny bit from where we finished with. So we've got code here, creates a list of 4 players. But this one, we've got a different function to let us put a player after a particular person in the list. So we can say, put a player after this one. You'll see why, because I want to order my list shortly. But so I say, put Zoe after the head. We scroll down a bit, we should be able to see the code. And I wrote a little bit of code for this here. I'm actually going to make this easier. This putting the array length there is nice to do. It's nice documentation, but it's not actually strictly necessary. So I'll just delete that just so we can focus on what we're doing. So insert after creates a new player, and then it says for the next field, make its next field whatever the next field is of the node we're inserting after, the element we're inserting after. And then says set that next field to be us. Does that work? Let's try it out, and then we'll have a look at. I've got it all here, so I can just do that hopefully. And run it, and hopefully we should see Zoe put after Anusha. Yeah, there we go. So Zoe's been put in our list after Anusha. You say, well, what if I want to put Zoe further down the list after Chicken? I can actually do that, I think. I could say get the next field of the head of the list and the next field of the head of that thing, of that item, and put Zoe after. Oh no, not there, sorry. That's not what I meant at all. Quite valid code, but not what I want. There. And that would put Zoe after Chicken, I think, if I've got it right. Oh, if I save the file. There we go. And there's Zoe inserted in the list after Chicken. So that's the insert after function. Alright. So it occurs to me I could just use the insert after function with the list. So I could just change this to use insert after, couldn't I? So we can just put something like that. That's what I'm thinking. Ooh. You can tell I don't use this editor a lot. So if I can get that, this is my idea. We'll just use insert after to put everyone in the list. I'm getting there. There's a big problem in this. There's a fundamental step we have to make here. Nothing wrong with that code, but it won't do what we want. It's got a major problem. It should compile unless I've made a mistake. No, I haven't. But it'll actually print out nothing. Oh, even worse. Not only doesn't print out nothing, it gets an error. I thought it would print out nothing. I was thinking that head would get to be here with null, but I forgot there's a problem here. What my problem is I'm saying insert after the head of the list, but the head of the list is null. So if we want to insert after null to mean put it on the head of the list, we have to do something special. We're going to have to. We've got to create a new head of the list and return it. And this is a common thing with operations to manipulate lists. So insert after is going to have to return a new head of the list if there's nothing in the list. Let me show you what I mean. Oh, let me show you the diagram of insert after what we've got. Well, actually, this is the case we're handling. Yeah, that's a good point. I can show you in the diagram. come down to insert. That's the looping. Oh, let's come on. So insert after, if we're working after a node, we can do this. We can create our node, slot it in, and put it there. But what if we want to put it on the front of the list? What if we want to add a node to the front of the list? Our problem is we've then got to change head and make head point to our new node, and then point to the old head of the list. So if you're inserting on the front of the list, you need to change the head of the list. So there's a big conceptual test step we're going to take there, where we change the type of this to let it return the head of the list. Now sometimes the head of the list is going to be unchanged, so we'll return the old head of the list. I need to change that up there as well. So if we've got to do one thing, otherwise we've got to do another thing. I guess we can do it here. How about that? Alright, what do we do here? It's the first item in the list, so we create a player, but its next field is going to be null. It points to nothing. And then we just return that new player. How about that? Ooh, I got an optimization here. How about I do that? That looks pretty good to me. So this handles a special case where we want to put something on the front of the list. And that should work. Oh, and then we have to use this here. There we go. Is that correct? Let's try it out. Let's save it and try it out. And there we go. Not quite doing what I expect. The order is a bit strange there, isn't it? So have I got the next field right there? So we put in Mark, then we add chicken after Mark, then we add Shrey after Mark, then we add Anusham after Mark, and then we add Zoe after Mark. Ah, it does do the right thing. Alright. Alright, so that's my insert after code. Adding a player to the list. Inserting it after the node we're pointed to. But notice for the special case here, where the list is empty, we'll actually get back a new head. Every other time, we'll get back the same head. All right. Be nice. This order's sort of random. It'd be nice to instead insert into alphabetical position, so keep our list ordered. Creates interesting possibilities if we order things. All through coding you'll find maintaining things in order changes what we can do. Sometimes lets us do things much more faster or more easily. So could we, when we go to insert, say Shrey, put them in alphabetical position after everyone else but before Zoe? When we insert Anusha, could we put her at the front of the list? Chicken second, Mark after chicken and before Shrey. Could we maintain alphabetical ordering in the list? Classic sort of problem. Insert an item into a list in such a place to maintain some condition of the list, maintain some principle for the list. So what can we do there? Alright, I've actually prepared a suitable prototype for a function already. We've got a couple of functions we're preparing to do. But let's put that one there. Say, can we write a function like insert after, but insert alpha, inserts it in the right player in the place in the list. So we'll give this function a pointer to the front of the list and then go down the list trying to find the right spot based on alphabetical ordering. So what are we going to do? Well, we're going to do something like this, aren't we? We're going to loop like this. It's going to go down the list looking for the right spot. Let's delete that comment, which is not correct. And here's where we need a new, more complicated stopping condition. We want to stop if we've seen a name after the one we're looking for. So if we're going to insert Shrey, we want to stop if we see Zoe. How do well, we could write a function that compared names, but we don't have to because it's a common task. And there's one existing already with the compact name of Strukum, which said at greater length would be string compare. It's a weird function because it takes two strings and it returns a negative, zero, or positive integer. Yeah, it's pretty common to be thinking, which one do I want there? Negative, positive. But I think we want to go down the list and say, while strucomp p name less than the one we're looking for. Alright, yeah, this is a little bit worried here. Alright. And I'm hoping we can do something like, well, let's try it out. Yeah, I've got various worries here. Let's try it out and just see what name we found. So we're hoping to do all of this. But this is getting a bit complicated to debug, isn't it? Alright, so let's see if we can just insert mark into alphabetical position. Well, let's even just see what the code does. We won't do anything, we'll just see what happens. See if we found the right spot to insert it in. And we'll just return the head of the list unchanged there. Oh, two problems. My arrow became an underscore, and I think we're getting a complaint. Oh no, we've included string.h. That may be the only thing. Not quite. Different name for list head. Getting close. Too few arguments to function of call. Oh, well, string comp. That's not what we want at all. What was I thinking? I think that's a loop that will stop if we see a name that's out of order. Let's try that out. What will that do? You can actually reason about what's going to happen there. And if you think about it, this code is destined for disaster and it breaks one of my cardinal rules. What have I told you about arrow? Every time you use a pointer, you use asterisk or arrow to go indirect on the pointer. So with structs we use arrow to say get the field that this pointer points to. You have to ask yourself, how do I know P is not null? And we will have to work backwards. We have to think backwards. So we can look backwards. Well, P's head's passed here. It depends on head being not null. Oh, here's our first call. There's head. Oh wait, head is null. So there's a problem in our code. We have to do something to make sure this doesn't happen. All right. So if we're going down to the list and we've got a null, we've clearly gone too far. So we've reached the end of the list. So let's try that. Try that. recompile and try again, and we should avoid this problem here. Bug fixed, program perfect. We got to here and P is null. Alright. It's clear here then we've got to handle getting this. It's interesting. What we'd need to know. So what do we do if we get here if P is null? Then we've got to create a new player. Something like this. How about that? Oh, we don't need the brackets there. That was Alright. I think I've got the code there then to handle that first case. Otherwise we'll see if we've got the right place to insert. If we get to P null, then there's no way to insert, so I think that's okay. And it's inserted Mark in the list. Look at that. And he's in alphabetical order. Also very good. Now it gets trickier. Alright. Let's try and insert chicken in the list. Alright, now I've got a problem. Chicken goes before Mark in our list. But we get to here and we've got P pointing at Mark. So our list has Mark, but we want to insert after whatever's before Mark. Interesting. So we really need to know the player before. As we go down the list, we remember it. So every time we move on, we remember what the previous node was. That may be good. So this may get us the node we want to insert after. So we go down the... Yeah, we need a diagram. Have we got a diagram? Diagrams always help. I highly recommend trying to sketch these things out always. Yeah. So our trouble is we go down the list looking for where we're going to insert. If we're inserting C, it goes between B and D. So our loop to go down the list, when P is pointing at D, that's when we've got to stop. But the node we want to insert after is that one. Why am I so worried about the node to insert after? Well, what have I got to do? I've got to change a next field to relink the list. So it's the crucial thing to know is the node I'm inserting after, not the node I'm inserting before. It's not symmetric. There is a way to make symmetric lists by using pairs of pointer, but that's you can do that in COMP1511 if you like. Just one pointer isn't complicated enough for us now. So if I go down the list, that's P. So I'm keeping a second variable, which was what P was last time around the loop, and before will be pointing there, and then I can use before to put C into the list. So loop stops with P there, but before is there, and then I can call our insert R function to put C into the list. So let's try that out. See if that code works. All right. We haven't quite finished this bit here. It's just printing out rather than inserting into the list, but we'll see what that does. We'll see if we can get chicken into the list. I think we're going to be good. I think I can get chicken into, if I manage to compile the right section of code. Oh, there's chicken in the list, but we've lost Mark. Oh no. That's a bit of a worry. What happened there? I think we can just go to create player, can't we? Maybe that would be better. Rather than insert after. Just create a new player. Make their next field whatever the head of the list is. And that there. Maybe that'll get us two things into the list. Gedit seems to be losing my keystrokes. That one. Bear with me. Oh, well, I've got the parameters to create player around the wrong way. Yes, it's best to try and keep a logical order of parameters for all your functions, otherwise you'll get confused about which way they go. Here it's okay because the types don't match, so DCC picks it up, but if the types match, that would be bad. Then you would have a subtle bug instead of an obvious one. There we go. We've got chicken and Mark into the list. We've got handling the special case when alphabetically the person goes first in the list, the player goes first in the list. We could see if we could do it we'll confirm we're handling that case properly. Actually, no. Let's be brave. Let's go straight to putting in someone who doesn't go alphabetically first. Let's go putting Shrey in, who will go last. So let's try that out. All right. So yeah, that's not very. That's a bit confusing, isn't it? Let me give you another piece of advice. If you put debug printfs in your program, put some unique string in there, so you know which debug. You get confused so often. Even expert programmers get confused like this, and it happens to students all the time. So you can put something descriptive in there, but there are all sorts of possibilities. So I've just put XXX there. So that's my debug printf saying we've got to here. We think we've got to insert this player after Mark, and that seems right. So we'll actually put the code in there then to try that. All right. So what now? Yeah, we'll call insert after. The before pointer and the new name. Yes, it's very annoying that these seem to have different orders to their parameters. Yeah, isn't that annoying and confusing? It's an example of poor coding style. Let's try that. Thank you, gedit, for finally saving my file. Look at that, Chicken, Mark, and Shrey. All right, so let's do let's do a couple of tests. Anusha, the front of the list, and then Zoe at the end of the list. Actually, we need another player, don't we? That's going to go in the middle of the list. A good test will be someone that finishes up in the middle of the list. And we've got Tom listening in on the call, so we'll put Tom, who should go in before Zoe. And after Shrey. Will all of those players finish up on our list in alphabetical order? And they do. Interesting. Alright. So there's insert in alphabetical order using this insert after function. And this. Yeah, I don't like the way that's written. It's not perhaps ideal. That would be better, wouldn't it? I prefer that. Alright. So there's two possibilities. We're going on the front of the list, and the player we create is the new front of the list, or we're inserting after some player in the list and we find them like that. Beautiful. Nice code. So that's getting our list into alphabetical order. Two big things I want to work on further in this lecture. One is removing a node from the list, and the other is freeing the list. Might do them out of order actually. We might do freeing the list first. It's in some senses a little deleting from a list is the hardest thing. So we might do that last. We might do free from a list first. If you remember a couple of lectures ago, I said memory allocation is put under your control with malloc. You say when you're done, you get the memory, and you say when you're done with the memory. If all these variables here, they have a fixed lifetime. They're created when the function is called, destroyed when it returns. And you don't have a choice about that. But you do have a choice here. Once you use malloc, it's up to you when the memory gets freed up, when it's done, when it's cleaned up. But if you, with this power comes responsibility. If you don't free up the memory, and it's a long-running program, and much important code is long-running, then memory will be steadily consumed, and this will create a resource issue. So for every malloc, we want a matching free. This is so important that DCC has a special feature to check if everything that got allocated with malloc got freed up. So we can run it. We can compile this program and then run it and see if that's happening. And it should be telling me that this. Why is DCC leak check letting me down there? That's sad. It's not noticing loss of memory. Alright. I'll check that later. Find out why DCC isn't reporting that memory is lost from that program. But what we need is a free players function.
Andrew, I think it's because the flag is -- leak check without the hyphen.
Alright, we'll test Tom's theory here. That was Tom Killingback, who's in there trying to spot my mistakes. And there are a lot of them to spot. Good theory, but no. I'm not sure what's happening there. I will try and I might be able to spot that during the break, but if I can't, we'll come back to that. That would normally point out that it should be printing a warning saying space allocated here isn't freed. Tools that do this, they get very complicated, but they're a big thing used by programmers to try and spot problems with their code before it breaks the world. Before, rather than have someone tell them, oh, your web server's not working, your e-commerce site is breaking. They like to run tools over their code over their code to find the things early before they get out and get seen by anyone else.
Oh, Andrew, the chat's picked it up actually. When you've run DCC, you're not putting it to an output file.
All right. So
actually, Adam picked that up. Well done, Adam.
Thank you. Oh, Adam's big shout out to Adam in the chat today. Who seems to be quite busy, and I'm not surprised. These are super complicated issues. Let me show you what's happened. If I do ls, I do a regular ls. All this file is up here, a.out. I don't actually know what the and the A stands for absolute, I think. Not that it really matters. Compilers, C compilers, for reasons lost in the mist of time, if you don't specify where to put the machine code, you don't say put the machine code in Battle Royale, they put it in a file called a.out. And up here I wasn't saying where to put the machine code. So alright, so Adam's theory is if I run a.out, the machine code I actually compiled. Actually, I'll show you a way to discover this. ls has more options. You can get more complicated information of ls, and it includes when the file was last changed there. If I look here, I can see at 10 to 2 I changed Battle Royale to C, but this was actually only changed at quarter to 2, and A.out was changed more recently. So you can look at those times and figure out, oh wait, I put new machine code in that file, but why hasn't it changed? So if you want to become impress all your friends, you can do that. But we'll try running the machine code in A.out and see if it does produce the warning about memory leaks. Oh look, there's the memory leak warning I was expecting, saying you allocated memory, Andrew, but you never ever freed it up. Alright, so yes, Adam's pointing out that it's the benefits of pair programming with so many friends. Yeah, I missed that from lectures actually. I missed doing having everyone there in real time, 5 meters away, shouting out, you've typed that wrong, Andrew. Oh, that's the problem. All right, so my idea is to write a free players function that will go down the list, freeing everything up. I mean, how hard can that be? And then we won't get this error here. All right, and it's seeming like it's going to be something like the print players function. So my sort of genius idea is to grab the print players function and use it. And we'll change print to freed. Look at this. This is genius level. And I can just change the printf to free p. Like that. And I can just make this free players. Surely this is... What could go wrong with this? I just have to say up here that that's a... Put the prototype up over here as usual. Got my function. Logic is impeccable. Got quality programming. Well, it should have a comment here, not quality program. That'll do for something resembling a sensible comment. Yeah. All right. Yes. So that, because I didn't say where to put the code, put it in A.out. That will put it in Battle Royale, the place we are putting it. Yeah. Look, compiles. What can go wrong now? Oh. Right. So this code, if you give it to a regular C compiler, maybe it'll work, or maybe you'll get an incredibly weird error. Now, DCC engages more tools to do extra checking, and again, as I said, programmers, much more experienced programmers, still try to use tools like this. They're just a bit more complicated than DCC. So DCC is saying malloc use after free. Yeah, that's not particularly helpful. So, yeah, it's not the best DCC message. What that means is, it says, what it's trying to say, and could say better there, is, Andrew, you told me this memory could be cleaned up, and then you used it again. So you said this memory, you were finished with it, and then you used it again. In a context like this, it's pretty harmless when there's a little program by itself. In more complicated context, this creates massive security. Well, it creates two things. It creates really hard to find bugs, and it creates security holes by malicious people who do really weird things to contrive to exploit this. So this freeing up a piece of memory but still using it is incredibly dangerous, and it's something we want to learn straight away how not to do. Now what did I do? I said, look, piece of memory that P's pointed to, I'm done with it. What's my next line? Now usually it's much more subtle than this. This is usually it's it's in 2,000 line code files, and they're separated in different files or whatever, and there's 5 function calls between them or something like this. Often it's really hard to find this sort of bug. It rarely sits there in such plain view as this does. But here it is. I'm saying free P. What's my next line? Saying get me the next field that P points to. And DCC is going, you told me you were done with the memory that P points to, and then you're saying get the next field. Let me go to a list diagram and show you that. I think we've got some diagrams. I think I've got some diagrams of freeing. It's further down. Alright, yeah, we're here. So we're at the first node. So yeah, we want to free this node, but then we want to go to there. But we can't get it from there after we're freed. Right. Let me do the sort of brute force and ignorance is what I call it, a solution. BFI. Oh look, I'll just swap these. But now that doesn't do the same thing, does it? No, that doesn't make any sense because P's changed. I can't swap the order. What am I going to do? And you can get stuck here, but this is one of these situations where you've got to think to yourself, another variable. It's a hard step to take, but another variable. So if I just create another variable, struct player, we call it anything, in equals P next. So we fetch a pointer to the next thing in the list from the piece of from what P points to. Then we say, we're done with P, and that then means we don't have to look at P again. So that crucial little step involves the DCC saying, Andrew, you're using memory. You've already said to me you're freed. Well, yeah. So I said this was easier. Yeah, the code's easier, but the concepts here are actually a little harder than deleting from a list, which we're going to do shortly. Don't worry. In fact, no, we're going to take a break, and then we're going to come to deleting from the list. All right. Have I got code now that will do the right thing? Let's have a look at my diagram here. Well, when I say my diagram, it's actually Mark's diagram. Mark's lovingly prepared diagram for previous terms. So I get the pointer pointing to the first thing in the list. Then what next? I get another pointer pointing, I get N pointing there. Oh, sorry, well, this is saying N pointing there. Oh, no, that's right. No, there's 2 ways to do this, I guess. Yeah. Let me clear this up. We get N pointing there. We call free for P, destroying that memory. Freeing it up, cleaning it up. But we've got N still pointing there, and that lets us move on down the list. So it's sort of a 3-step thing. And that should finish up, should go down the list freeing 3 things. You're saying, how can I see that happening? I'd like to see that happening. You can see it happening with a printf. You can say printf %p. You can just use that to print out a pointer. Oh, actually, what we print out though is the player name. So we could say freeing up %s and print out the name of the player we're freeing. Yeah, that'll work. So that should show me going down the list, freeing up those player names. And it should show me leak check reporting use of undeclared. Here we go. Here we go. Will it free up successfully the whole list? Alright, so I've successfully run leak check, put the machine code in the right place this time, created a list with Anusha, Chicken, Mark, Shrey, Tom and Zoe all in the right order. There. Even though I said insert Mark, insert them in a random order, I got a list with them all in the right order, printed out by print players. And then I called free players to free up the memory, and I added a debugging statement to say who I was freeing up, and that runs down the list, freeing them up one by one. And we get to the finish, and DCC is, there's no message to say, great work Andrew, you freed up all the memory, but yeah, no news is good news with DCC leak check. It's saying, that's good. Of course, if you run leak check with a program that doesn't use malloc, it will print out nothing as well. But we're using malloc. We've created a list, we've freed it up. We should feel happy with ourselves. Okay, we're going to take a 5-minute break now. You can stand up, go outside in a COVID safe manner, and look, stretch, relax those eyes, and we'll be back in 5 minutes. I'll answer any questions they have about this code, and then we'll move to the second half of the lecture, which gets more complicated, where we have to delete from the list. Well, the code's more complicated, perhaps the concepts are simpler, we'll see. But anyway, we'll get to the next part of the lecture. Alright, so back in 5 minutes. All right, hello everyone. We're back. Sorry, my webcam wasn't working. It's an annoying thing with Linux. You can only have one program at a time reading a webcam, and I accidentally set it. Had another program reading it. Tom and I were trying. Tom had came up with an option that might have made it work, but we're fiddling about for far too long. So you just have to put up with not being able to see my face for this lecture. All right. There's an excellent question Tom has passed on about. So malloc gives us this memory here. So it gives us, and that might be, I don't know, 120 bytes of memory, say. What do we know about what's in that 120 bytes of memory? Is it, for example, already 0? Is any pointer value we've got stored going to use assumed to be already null? Can any int that's in, if we have an array of ints, can they be assumed to be 0? The answer is no. You don't know what's in these bytes. You've got to put values in these bytes. So what I'd say then, I guess the way I'd say it is the memory is uninitialized. So malloc gives you uninitialized memory. And you think, oh, that's a bit annoying. Couldn't they do it? Couldn't they be more helpful there? And you can write code that sort of does that. It's not making it really work everywhere and bulletproof is complicated, and so it ends up for a lot of coding. You have to do the initialization yourself more or less. So it's probably better to get into just the habit of initializing the memory. So when we create a struct, typically the first thing we do is go and put values in the fields, and there might be zeros, there might be nulls often. In this case we're putting in more interesting values, but yeah, you've got to initialize that. And that comes up a lot with the assignment too. Assignment 2, it's maybe number 1 in mistakes students make is like malloc some memory. So I've got a pointer to it, yay, great, but they don't initialize it properly. They malloc memory for a struct, but then they don't put values in the fields of the struct. Don't put appropriate values in the fields of the struct. DCC actually gets quite clever here. It puts a weird value in the struct, in the malloc's memory, and if it ever spots that weird value, it thinks, they never overwrote it. So DCC tries to detect you doing this. But that's an example of DCC doing these things that trying to help programmers, and where we have tools to try and do that. All right. Maybe I didn't explain it clearly. Yeah. The question I get a lot from a lot of students when they click with this is, well, why doesn't malloc just put all zeros through there? And yeah, that's sort of helpful, but it's not always what you want. So, and is all zeros if it's a double, is that what you want? If it's a pointer, is that guaranteed to be a null pointer? They get into weird and complicated questions. So it's not that hard. We've got a struct of 2 fields, we just fill it in. It's not that hard for the assignment. You malloc a struct and you fill in a couple of fields. All right. Yeah. What was I up to now? I've created this list of 5 things. We're working along to this game. I wrote a free program. Freed up all the things in the list, with an extra printf in there just to say what we're doing, and a little trick here to avoid. We need the next field in the item. We want to free it up and then go to the next field, but we've got to save it because we can't. If we free it up, we can't go back there. Yeah. Free all amongst this. If there's time, I think there's probably just time in this class. I might come back to a nicer way to write that function, a clever way, but this is the more obvious way. My next task is is this whole game is we start with a list of players and then we toss them out one by one. And the last player left in the game, if chicken's last in the game, chicken wins. So we might want to toss Shrey out of the game. So how do we do that? So what I want to do is something like this. I want to write a remove by name function. Is it remove by name? No, remove player. That's the one I want. Yeah. That's actually that's the function I wanted to write. I'll come to remove my name. Remove my name is the next function I was thinking of, which gets the player to remove from standard input. But we'll come to that. That's the last part of our little puzzle. So I want to remove a player from the list. And again, it's got this really weird thing is I'll give the remove player the head of the list, but it has to give me back the head of the list because the head of the list might change. So if I remove the first player in the list, the head of the list will now be the second player. If I remove the second, third, fourth, fifth or sixth, the head of the list doesn't change, but we still end up with this weird thing where we insert we remove some where we in the special case where the head's changing because of this action, so we have to return it. Alright, so we'll try it out. We'll try and remove Shrey and print the players out. So we need to make it clear that we're printing out the players for the second time, so we'll just print out. Oop, that's probably too many dashes. Right. Let's try all of that out. We can leave checking on, doesn't matter. Actually makes our program run a bit slower, but that won't worry us. So we'll run this. Oh, we need to print the players out again, don't we? So I'd like to see this print out with Shrey removed. In fact, yeah, that freeing is that we'll comment this out because we know that was a debugging thing. All right, run it. Right. There's our list of players printed out. Let me scroll up a bit and further. Then we called remove Shrey, printed out some dashes, and printed out the list again. With Shrey still there. Oh, alright. How do we get Shrey out of the list? Again, we've got some code that sort of will do the job for us. This insert alpha code looks really relevant actually. Let's put it here. Oh, yeah. All right. So what we're looking for is remove name to match p name. We want those two, if they're the same, then we're at the node we want to remove. Okay, and this before pointer, maybe that's useful, so we'll keep that bit. So we finish up with two things. We finish up with a pointer to the node containing the name and a pointer to the node before it in the list, and I'm thinking that might be useful. Alright, so I'm repurposing code. Now that was before an alphabetical order was less than 0. We want to match strucomp. I can check the manual entry here. strucum returns 0 if they match. It's not the easiest thing to read, is it? But strucum returns 0 if this string and this string, they're the same characters. We're not actually doing anything here. What should we do to find out if it works? Let's print out the name here. There's a bit of debugging. We'll put found on it. There, found. We'll print out the name. Is P not null? Yeah, interesting question. But we're debugging. If it breaks there, it breaks. Oh, and we're getting a message we're not using before P ever. That's okay. We might yet. We could comment it out, but let's run the code and see if we find Shrey. Oh, we found Anusha. That's a bit of a worry. We're looking for Shrey. What did they get wrong? How come I found Anusha? How strange. What's my loop condition? While P not equal to null. Yeah, it must be this failed. So I want to keep executing while P is not equal to null. And what? Ah, have you spotted my problem? That was an accident, but it's well, maybe there are programmers out that don't make this mistake, but this is a mistake I make regularly. I've flipped the logical sense. I want my loop to execute while P. Well, I could exploit the fact that the loop's in order, couldn't I? Yeah, interesting. I could do that. But I want to, well, we've not found the name. So I want to stop if we get to the end of the list, sure. And I want to stop if the name matches. So I had the sense wrong, not equal to. While P is not equal to null, and while the names don't match, go down the loop and keep tracking the pointer before the one we're looking at. Let's try that. So found Shrey. Let's check what. Let's print out the name before. So again, no guarantees this is not null, but this should be pointing at the node before Shrey, which is Mark. So I'm hoping that will tell us that found is the with P. Right, let's see. Let's make that P. And before points at. See if we got that right. Yeah. P points at Shrey, before points at Mark. Let me switch to my. I have a diagram. Way further back. Ah, all right. Sorry, they've got different player names in it. But that doesn't matter. We want to remove this one. Ah, it's nice. Yeah, we want to. This is Shrey in our example, not Eng, but we want to remove this node. How do you remove this node? Ah, it looks pretty easy. I can take that out just by going. So I just have to change Mark's next pointer to be the one after Shrey. I can do this. If I say so before is pointing at Mark, before next equals p next, that will just dump Shrey out of the loop. Shrey is gone. You see my plan? I'm saying take this pointer value here, put it there, so then the list will do that. Go right round Shrey. Let's try that out. Oh. Let's try spelling things properly. Oh, we'll dump the underscore p. I never like that. Well, it's a good news and bad news situation, isn't it? The good news is we dumped Shrey. Well, maybe that's not good news. Well, no, he shouldn't be playing games. He should be focusing on running the forum for us. So that's probably good. The bad news is we've got a memory leak. DCC minus leak checker saying, Andrew, you allocated memory and you never freed it. Which is weird because I'm still calling free players, but I'm freeing up the players now in the list. But Shrey's no longer in the list, is he? So he's no longer getting freed up. So that's... I took this round here. Shrey's then sort of off there with nothing pointing at him. If you're a malloc memory with nothing pointing at you, you can't be freed. You got to be careful about that. So what can I do with that? Of course I can do this. Free up Shrey. Say, we're done with Shrey. Hopefully if you're quick you're saying, wait a minute Andrew, wait a minute, I'm too late, I'm running the code. And we're back to a different error, use after free error. And you're saying you didn't learn from your previous mistake. Yeah, I used p here. I said I'm done. I'm free up the memory for p. Then I said look at the next field in the struct that p points out. What was I thinking? But I can use the same trick here surely. Struct player star in equals p next. Save whatever is the pointer we need, fetch it first, then free up the memory, then just make this. Alright, no memory leak, Shrey gone, no use after free, perfect code. Let's have a look at that. Look at that. Brilliant. We've deleted Shrey from the list. Alright. What now? What happens? What special cases do we want to handle? I guess we've deleted Shrey from the middle of the list. Before we go any further, we might try a few cases. What cases do you think we'd try? I can think of two obvious ones. Zoe, who's the last one in the list, or Anusha, who's first in the list. So let's see if they work. So let's try deleting Zoe instead of Shrey. Does that work? Ah, brilliant. Zoe gone. Alright. There is, by the way, another case that you might want to think about. But Anusha? Let's see if we delete Anusha. Does that work? The first player in the list. Oh, well, it's my debugging statement that's died. What's my problem with my debugging statement? It's actually failing to print out before. Oh no, it is. There it is. Before is null. DCC is saying, this line, Andrew, you've got a problem. What's your problem? Accessing a field via a null pointer. And sure, it prints out some variables for my debugging joy. It says before is null. That's actually Alright, so we'll get rid of our two debugging statements. So we've still got a problem here, haven't we? Because here we're changing that field. And before is null. But our problem is we have to change the head of the list if we delete the first thing in the list. So we've got two cases to handle here. Let me go back to my diagram. If we're deleting Aang or Goku, yeah, we change the pointer before. But deleting the first thing from a list, we don't change a struct at all. We change the variable we're keeping the head of the list. It's an annoying special case, isn't it? It's an annoying thing about linked lists, that dealing with the first thing in the list is a special case. So if we want to delete the first thing in the list, we have to change the head. Now we were thinking ahead. Yeah, all right, I won't do that again. We were thinking of that when we had this return what the head of the list is now. So we've just got to handle those two cases. I can do this. And we should we would have, if we'd been thinking about this, we would have got to that idea. Remember, I said every time you use an arrow, you ask yourself, how do I know that pointer's not null? If you can't prove to yourself that that pointer can't be null, then you probably have to add code, an if statement, a while statement. Something needs to change. So we need to add that. So if we're deleting the second, third, fourth, fifth, sixth thing in the list, we can do that. But if it's the first thing in the list, we're going to do something else, which is return that as the new head of the list. I think I've got it. I think that will let me delete Anusha from the list. Fingers crossed. Look at that. All right. Any more special cases? Yes, RIP. Well, now it's RIP Anusha. So I tried deleting Shrey from the middle of the list, Zoe from the end of the list, and Anusha from the start of the list. You can sort of get into second order things. So you might try deleting Zoe and then Tom to delete two things from the end of the list, or now deleting Chicken and delete two things from the front of the list. But there's a huge missing test case I've missed. And hopefully some of you are spotting it. Hopefully some of you at home in your bedroom with your laptop leaping up and down saying, well, wait, what if you delete someone who's not in the list? I'm not in the list. What if we try and delete me? Alright. What happens if we do that? Think about it. A lot of you are smart enough. Well, no, you're all smart enough. Some of you are grasping these concepts quick enough to figure this out now. Some of you, it's going to take a week or two. But try. What happens with that code? So it says delete Andrew, but I'm not in the list. What does that mean? That means strucomp there is always going to be not equal to 0. So it's as though that doesn't exist. The strucomp is always that's always going to be true. Strucomp not equal to list. So we're going to get to the end of the list. So this loop's going to finish because P is null. What happens if P is null in that code? Look here. We're using that. We're saying set N to be the next field or whatever P points to. And again, you're coming back to my rule to make your life better. Every time you use a pointer, you should be asking yourself, well, how do I know that's a valid pointer? How do I know that that points at a struct? How do I know that's not null? And I don't. The loop can terminate because P is null. And we can get to there. So I've got to do something different if P is null. Okay. My function's looking a bit messy, and it's possible if you thought about this, you could restructure it to be better. But something I don't worry about. I'm more worried about you thinking logically about all the cases than producing an immaculate piece of perfect code that's minimal in every way. So here's my thought here. If P is null, well, what do? We probably want to do that, and maybe we want to print a message out. A warning. So we'll return the head unchanged. The list hasn't changed. We couldn't delete anyone because of that. And we'll say the name you asked me to remove does not exist. So warning, Andrew not in list. Look at that. Alright, so I've worked through those in isolation. Let me then try writing a different function. The next function I wanted to work on is this one. Yeah, really should put a comment at the start of that function, shouldn't they, to say what they are. That could be a better comment, but that will do. And this one, read a player name from std_in and remove them from the list. All right. I can do that. Actually, it's not necessarily the head. It's not. It's resume the possibly new head of the list. That's what I want, isn't it? That's getting to more like a reasonable comment. Okay, so this code's actually pretty straightforward. How do I what would we call it? our name, and fgets is our function. Can you remember the order of the 3 parameters to fgets? I often forget, even though I've used fgets so many times. Fgets, it is char array, size of char array, where to read from, which stream to read from. And we only ever use one in this course. So it's our name, max name length, and stood in. Oh, let me show you a. If you wanted, you could actually use size of here. Is that better? Yeah, it's sort of. It's an interesting question, but you could use size of there. We won't do that. We'll keep our code just super obvious. Fgets. Oh, whenever you read something from a user, you probably should have got a message. Player name. Well, name of player to remove. How about that? So we print out a message. Name of player to remove. We read it in. And then we call remove player. Then we call remove player to remove them. And that returns a new head, and we in turn want to return it. So I think in 4 lines, this is the function I want. It's beautiful. Well, it's got some spelling mistakes, and perhaps I shouldn't get too excited until I've done at least a little testing. But I want to be able to say remove by name and just give it the head of the list, and then I can type in Zoe if I want to get rid of Zoe, or Shrey if I want to get rid of Shrey, and so on. What could go wrong? Let's see if it compiles. Compiles. Name of player to remove. Alright. Actually, let's remove chicken. Hit return. Chicken not in list. Oh, that's weird. Let's try again. Let's try to remove Shrey. Shrey not in list. What's going on here? Now, some of you might be spotting the problem there from the output there, but let me show you a debugging trick that's quite useful with strings. Problem here, by the way, it's non-printing characters, and non-printing characters are a little hard to see. So we want to put markers there so we can see exactly what the percent is not in the list. Maybe there's a couple of extra spaces on the end of rem name. So if we put markers round the string we're putting, we can see any extra spaces or things like that more easily. What marker characters would you like to use? We could use, you can use anything you like. So we could use 3 ampersands if you wanted. That's a bit silly. We'll run that. We'll put in Shrey. Oh. Well, you can see the problem even though I mistyped Shrey. The problem is here, isn't it? Now what, by the way, the marker character I'd normally use, and it's a bit confusing, I guess. Oh, that's it. Now we'll leave it at 3 ampersands, that's fine. I'd normally put a single quote there, but that often confuses students with the special meaning of single quotes elsewhere. But as long as you put some characters there, you can put ZZZ, whatever you like, just so that you can see exactly what's in the string. And our problem is a new line in the string. So what's happening there? Well, we go to man fgets. It actually does warn us. If a new line is read, it is stored into the buffer. So we're reading shrey new line. We're getting shrey new line. And the trouble is when we do a strucomp, we're comparing shrey new line to this. We're saying, all right, I've got a genius level brain. I'll do this. I'll put a new line on shrey in the list. Yes, you could do that. It's not a good idea, but let's do it. And now we can remove shrey from the list. You'll see we get an extra new line printing out here. But now if I say remove shrey with no new line, the extra new line will match shrey with a new line. Yes, that's too stupid for words. Maybe you should forget we ever did that. Not a good idea. What we really want to do is get rid of the new line here. How do I do that? Oh, I know how to do it. Just watch me. Alright, so it's shrey, 5 characters. So if I do this, I'll put the 0 marking the end of the string in array element 6, and that'll terminate it there. So we'll have exactly shrey. So that will let me remove shrey from the list. That's what could go wrong with that. Good solution, Andrew. So I'm typing shrey. Look at that, it worked. Genius level. Alright. Now, hopefully you've spotted the slight problem there. Shrey has 5 letters in his name. Sadly, no one else does. So if we try to remove chicken from the list, that's not going to get rid of the new line from chicken new line. It's going to go to array element 6, which I think is the E. So we're going to try and remove chick from the list. Warning, chick not in list. Alright. So I need to know how many letters are in the name. And there's another function to our rescue. Strlen. Strlen will tell us how many characters are in the name. Calculates the length of a string, not including the 0. Equals strlen rname -1. So if I've got this right, that will, you're saying y -1. Strlen counts the new line. So if we have shrey new line, it'll count 6. 5 for shrey's name and 6 for the new line. So I say to strlen, how many characters? And subtract 1, that will get rid of the new line. Removes new line from the count. Then to that array element, I assign null. I think I've got the new line done. In fact, I'm overwriting the new line. If I looked in this array element, I'd find the ASCII code for new line, which is just at 10. I'm struggling to remember. I don't need to remember. And I'll overwrite it with a 0. And remember, 0 is the marker of the end of the string, so that's our little programming trick to stop the string early. Alright, So let's try this. Does it work for Shrey? Yes, it does. Does it work for chicken now? Look at it. Oh, damn it. I haven't. It's just frustrating. Let's try it for chicken. And it does remove chicken. And Nusha, he's gone. Look at that. Oh, that is great. Alright, there are a couple of things wrong with this code which I'm not going to correct. A careful programmer, a paranoid programmer, a good programmer would check to see whether fgets managed to read something, and a careful programmer would check there to see whether it managed to read a new line. So it would only overwrite this character if it was a new line. You can do that with just an if statement though. Alright, so I just need to add this to a list, to a loop, don't I? If I can find my at this point. Where are we? Here we are. So oh, well, while what? I don't know. Alright, I'll say while head not equal to null. How about that? It's not quite the right stopping condition, is it? How about that? I've got a loop now, and I can delete players one after another until the list is empty. Oh, that's pretty good. Let's see if I can manage to throw away all of that stuff. Recompile. Let's first see if we get. Come on, gedit. You know you can save it. Maybe you can't. Uh-oh. Now I'm really worried. Why is it taking gedit ages to save a file? Oh, it seems to have done it. That's a little worrying that saving a file should not take that long. Alright, let's see if we can have a game to the death. Well, first out is... Actually, we'll toss Tom out first. Sorry, Tom. We'll get rid of Zoe. Zoe's gone. Anusha is gone. Mark is gone. Shrey is gone. Oh, it should stop now with chicken as the winner. But Battle Royale is meant to stop when there's just one player left. How am I going to do that? There's a few possibilities there. It stops when there are no players left. Right, let me show you my idea. If a list has one thing in it, the next element of the head is null. So while the next element of the head is not null, will that stop with just one player left? Come on, save my file. Well done, GCC gedit, saving my file. We recompile and we try running. Alright, a battle to the death. Zoe's out first. Shrey's out second. Mark's out. Anusha's out. And it's just chicken or Tom. And I'm afraid you go, Tom. And chicken is the winner. Yay. Oh, we could even print out a winner, couldn't we? The winner is Now, all of this code, by the way, depends on the list having at least one thing in there. So yeah, there's always more things to think about, more things to check, isn't there? But there's printing out the winner of the game. I'm going to ask Tom to scan through the chat and tell me if there's anything that we should try and wrap up on. We're actually going to come back to this example and refactor it and improve it a little bit in the next lecture. Not a lot of code to it, but let's see if we can print out the winner. Alright, this time Anusha goes first, then Mark, and Shrey, Tom, and then Zoe. Oh, what happened to Shrey? I must have misspelled Shrey. Oh, there we go. And it prints out the winner chicken. Okay, Tom, in our seconds left, is there anything I should address?
Nothing in particular in the chat, just someone pointing out that you could also use an if statement inside the while loop to check if it's the last person.
You could. There's always multiple ways to write this. It's not a bad idea, by the way. It's a mark of a successful student. You see an example like this in a lecture or a tute or a lab, to get this code and say, oh, well, what if I put an if statement here? Couldn't I do that? And you'll discover, oh, yeah, that works. Or, oh, no, I hadn't thought about that. Or I'm not thinking about this quite right. This is the beauty of doing this course versus maths, is it's so easy to check your understanding of things by just running the code. These days, of course, you've got things like Mathematica and so on, all these mathematical tools. You can check your understanding of some maths things, but it's dead easy with coding.
And if you wouldn't mind just showing the remove player function again, just for a moment.
Let me scroll down and show the remove player function. Yeah, there we go. And I'm going to change those ats, they're annoying me. Yeah, so there's the remove player thing, and it's the same idea. We go through the list, and we've got two possible reasons the loop will exit. One is we'll get to the end of the list. The other is we'll find a player matching the one we want to remove. Strucomp returns 0 if it matches, so we want to loop while this is not 0 and while we haven't got to the end of the list. Yeah, it's a complicated condition. This is hard. This is as hard as it gets in this course in trying to explain code, this sort of stuff. This is super hard for someone who's been coding for only 8 weeks. So yeah, you're going to have to put some effort into understanding this. The other thing is we've got this second variable, which is one element in the list behind the one we've got tracking on the list. So P goes down the list one element at a time, and before is always pointing to the element before. And if P is pointing to the first thing in the list, before is null. If we get down here and we never found what we're looking for, we do that. Otherwise we've got 3 cases. We never found what we were looking for. The thing we want to remove is the first thing in the list. The thing we want to remove is the second, third, fourth, fifth or sixth thing in the list.
The other thing I'd say about linked lists is it's often, I find it super helpful when you're trying to figure out what you should do, is to just draw on a piece of paper.
So you have a piece of paper beside you like this, and you sketch it out. You say, oh, P is pointing there, and it looks like this, and the next field contains, sorry, my handwriting is appalling, but the next field contains this, and the name is, so you write little boxes for every struct, you draw arrows for the pointers, you connect them up. So yeah, a bit of a paper is actually often, well, a second screen and MS Paint I guess is probably as good, but a bit of paper is the low-tech way to do it. And so often when a student asks a question in a help session or whatever, you'll start sketching out on paper, and before you finish they'll say, oh wait, no, I'm going away now, I see the problem.
Yep, absolutely.
Alright Tom, anything else?
No, I think that's all from the chat and all that I can think of as well. Yeah, diagrams for me with linked list really make the difference.
All right, so we'll revisit this and go through this a bit. We'll also restructure it and look into .h files and .c files and maybe do a type def as well to show you that at the start of the next lecture. That was the Teams announcement for my next meeting. it's no end of fun. So a huge thank you to Tom in the helping me out, correcting my mistakes and so on. Everyone in the chat, particularly Adam for answering all the questions so patiently in the chat. Oh, and a big thank you to Zoe and the other Tom for the live stream yesterday. By the way, the tutors got together in a marking party, which seems to be a bit of a contradiction to me, but they got together last night to figure out how to go about marking all your assignment ones. So that's in progress. So hopefully you'll have your assignment ones back fairly soon. All right, so I'll see you all next Tuesday. Please stay COVID safe until next Tuesday. Well, you've got assignment 2 to work on, you've got lab exercises to work on. You've really got no reason at all to vision and exposure site, except maybe food, I guess. All right, so I'll see you all then. Thanks for listening in. What I want to do is in that.